Oh, like I was told that the calculations to verify the positive discriminative theorem graphs are quite technical and complicated. So I thought to start today, I'll just briefly write them down for in a sort of very simplified fashion for those interested. And as you should see, they're tedious, but they're also a bit uninformative because it's kind of the regime where we are not really interested in. Because it's kind of like a rounding error. The positive discriminative of theorem graphs is linear and not maybe zero as one would expect. That's also actually very convenient because that really guarantees that the inverse relation in the Boppana scope can even hold because we need the product to be of the order p times n cubed. So b is part of the problem. So how does it work? For simplicity, let's assume that n is multiple of r. Actually, let's assume it's multiple of 2r, so the edge density can be expressed. So the point here is that the edge density is 1 minus 2k minus 1 divided by 2rk minus 1. This is not quite 1 minus k, but it's something like 1 minus 1 over r plus constant over n plus something that is proportional to 1 over n squared. So for example, for complete bipartite graphs, which are perhaps most into it, like here we don't have the r floating around because r is just 2. We know that the edge density is n over n, 2n minus 1. So this you can write as a n minus half over, sorry. What do I want here? Yeah, well, n minus 1 or 2n minus 1 plus 1 over 2n minus 1. So it's half plus something that is of the order 1 over n. Now, the point is, if we take a smaller complete bipartite graph, so if you have a set U of size 2k or 2k plus 1, the way to maximize the number of edges in it is to pick a complete bipartite graph of as balanced size as possible inside kn. So let's focus on the case when you use kk. Then the discrepancy of u is going to be k squared minus this edge density times 2k choose 2. So you're not going to get k squared minus half 2k choose 2, but rather k squared minus half plus something constant over n roughly. So if you now do these calculations and actually carefully work out how do these error terms interact with each other, you get a here, which is something if our sets u has a linear size, it's going to be linear. 2k minus a, again linear, assuming we are not of size n minus little n, dividing by something of linear size. Remember r is constant. So this is always at most linear. And if we pick u to be constant size n for any constant c properly bounded away from 0 and 1, then this expression actually grows properly linearly. So that's why we get linear. It's kind of like you really have to write down the numbers. It's a mess calculation. It's not particularly instructive. We don't care about, but it's because of the rounding errors that you actually get linear positive discrepancy for the wrong graphs. Okay, so today's goal is to prove the following theorem. And while this might not be the most sort of well, this is interesting on its own right. One of the reasons why I want to give the proof is that the proof techniques also apply in a bunch of other instances. For example, you can use them to prove that by using one sort of crucial lemma, you can prove the discrepancy, so the maximum of positive and negative discrepancy is at least square root of that, and that's basically how the standard proof of that fact goes. You can also do some hypergraph variants, which are not necessarily tight with that same argument and so on. So what's going to be a key lemma in the proof? So, okay, so first of all, we again, as usual, assume that P is probably bounded away from 1 over n and 1 minus 1 over. This is actually the only place where we use this assumption. All the rest of the argument would carry over, I think, for general densities as well. And let X union Y be a random bipartition. Then I claim that if we for each vertex X in X, we look at how many neighbors does it have in Y. Compare that to the expectation, so P times the size of Y. Take the absolute value, so the standard deviation of it, if we view it as a random variable, and sum them together. We claim that the sum of the standard deviations is pretty large. And why is this going to be useful? Because it means that there are basically things in X which is much more, because the average should be 0. It means that we have things in X which is much more neighbors in Y than they should, and also things which is much less. So we would be tempted to move some of those vertices from X, Y, to boost the positive discrepancy of Y. And also that kind of like implies that if we shuffle those vertices around, then we could also construct larger cuts, for example. So the same technique can be used to lower bound the surplus of a GNP. So this beta is going to be some constant not depending on P. And what we get here is square root of this expression. Okay, so what this statement is roughly saying is that on average, this should be roughly root P times 1 minus P times n for some constant beta. So let's now assume that P is less than half. So, which is always fine because we have this nice property that the positive discrepancy of G complements the negative discrepancy of G, and so on. And it's also much sort of more intuitive to work with sparse graphs than graphs whose complement is very sparse. So we can basically think of this as bunch of 0-1 random variables with average P. So for each suffix vertex X, we look at first of all, we take the indicator for function is X in X. So yeah, let me actually write it down. So so this sum is the same as summing over all the vertices. here we basically did nothing because we just restricted our attention to those x and x. And if x happened to be in y, x, this minus x doesn't matter. If it's in y, it doesn't matter either because we are multiplying by the indicator function of x and x. The good thing is that this bit here only depends on the status of where these all the other vertices than x are located. So basically, these are independent random variables for the random input. So and the expectation of this is half, so we can just worry about the expectation of this guy. And now, what's the expectation of this guy? The expectation of this guy is we basically sum over all the vertices B which is not in X of let's write rho B for the indicator function that B is in Y. And EV for the indicator function that Bx is a pitch. So the first one is clearly their product because it means that Bx is an edge and B is in Y. And the second one is just P times rho B.
So what's this quantities in the parentheses, or it's the whole thing you're writing?
It's this guy
Okay.
for X, for fixed X. So what my aim is to sort of give you because I think proving this lemma doesn't make too much sense, but I'm just trying to give an intuitive reason why is that of the order root Pn when P is less than half. And basically the expectation of EV is P. Because it's the edge density. Okay, so let us write PB as 2 epsilon v minus 1. Why is this useful? Because PB is 0, 1 random variable. And it's both of these are attained with probability 1/2. But for concentration inequalities, we basically want to look at the sum of these random variables. It's much more natural to scale them so that they are plus or minus 1 random variables because then the mean is 0 and it's symmetric around the origin. So we just do a very simple substitution. No, sorry. So I want to write epsilon v to be 2p minus 1 because then these are IID plus or minus 1 variables. So rho v is epsilon v plus 1 divided by 2. So now this is going to be okay. Now let's have a test. Are you with us? So what is this first term? The sum of EV minus P over all the vertices V which are not equal to X.
Degree deviation.
Second term should be half times.
Yeah. Excellent. But this, how much the degree of X deviates from the average degree. What it means that, and also remember, this is now symmetric around 0, because these epsilon v's are IID plus or minus 1 random variables, because they come from maximum. So we are trying to figure out how large is the expectation of this absolute value. So if the degree deviation is already large, we can just ignore this bit, because it's a large constant plus some random variable which has a distribution symmetric around origin. So the expectation of the absolute value of this guy is at least this constant. That's a useful bound if the degree deviation is large. Okay, so very informally, we can assume that the degree deviation is small, and let's be bold and actually assume that the degree is exactly p times n minus 1. The actual sort of, it actually does you do a little bit of sort of an optimization problem, but it's like, in reality, you can bound that this expectation for fixed x is bounded below by half of the degree deviation plus the expectation of this sum. So we basically want to show that some linear combination of these two is large. Okay, so now let's look at the second sum. Now we can ignore the half because we only care about these things up to constants.
I'm confused. You are in
I want to bound expectation of absolute value of this guy.
oh, okay, see.
So what I've shown, so let's call this A. So now A is the degree deviation, or let's write it to A. There, this guy is, let's say, B. So now this is going to be the expectation of B. So let's label the vertices so that the neighborhood of X is V1 up to VD. Here, D is just D of X. And X itself is Vn. And here are the rest of the vertices. Following the expectations around here, but let's be add them back. So I claim that we can just ignore the second sum.
Write down the first formula.
Sorry?
So, what is the thing between?
Yeah, here I should be summing over B. Let me write this again. So the very top order should be written as this. It's the second time of the sum multiplied by 2. So remember, our expectation split into two of these sums. Here we have the degree deviation, and here we have the rest. And now we are trying to prove that the expectation of the rest is large, provided that D is large. And so what we did here was basically we tossed away the second random sum and claimed that the expectation of the absolute value of this whole sum is at least the expectation of the first term. And here we use the same argument that if we call this x and this y, then the expectation of x plus y, the absolute value of it, is always at least the expectation of x whenever the distribution is symmetric of the origin. Because basically, whatever values we assign, like if we condition on the value of x, then whatever noise we add with y, then it achieves the value a. I mean, here we are dealing with discrete random variables, so it's very simple because for any a, which is in the range of y, we know that y attains the value a and minus a with equal probability. So then in the expectation of the absolute value of x plus y given the absolute value of x, we have a tensor for absolute value of x plus a and absolute value of x minus a, and absolute actually with both of them with absolute values, and then by triangle inequality, the average of those is at least as large as the absolute value of x. But here we are just taking the absolute expectation of some of the DIID plus or minus 1 random variables. So that's well known to be proportional to square root of D. So this is actually exactly, because remember P is constant. So what we concluded is that the first term is the degree deviation. The second term is bounded below by something that's roughly root D. So when we bound the absolute value of the sum, the expectation is the absolute value of the sum, and here we are using the fact the distribution of this is again symmetrical around the origin. It's pretty much at least the maximum of these two guys, which again is half of their sum. So essentially what we conclude is that this expectation is at least the sum of the degree deviation plus something that grows proportionally root D. And as long as P is at least 1 over n, and at most half, this is minimized exactly when every degree is around P times n, in which case this term is 0 or close to 0, and this term dominates. So for every vertex, the contribution is root P times n. And then when we sum them together, we get root P times n, which is exactly root p times n cubed. Okay, this is just a sort of a intuitive level. The formal details are a bit sort of a mess, and I don't want to waste too much time doing it. Basically, if you want it, I think you could fill in the gaps. Proof is actually fully written in the notes, so they will be on the website like during this afternoon. So if you really want to see the details, go and have a look. But this is just a technical tool which is useful, so I don't want to waste too much time proving it. Basically, the bottom line is that you should really think of this as a sum of IID sort of plus or minus one random variables, or rather the weighted average of them, and there being d of them. So basically, this then corresponds to the standard deviation of the. I'm really bad at distribution. I think it's the Bernoulli distribution, each some of them. So this is kind of like it's nothing magical with root p times n appearing as the
x plus y thing again. So to claim that
it's basically condition on the expectation of x.
yeah, but my question is why is that so? If I understand correctly, your y is that the sum of p times epsilon I, right?
Yes.
So why is that symmetric about 0?
Because every epsilon I is IID plus or minus one random variable. So if you take a sequence, your favorite sequence of epsilon i's, then the negation of the sequence gives you the corresponding negative value.
Sorry, what is epsilon I is
Plus or minus one random IID random variables. Because rho v is a 0-1 random variable, and because we like working with plus or minus one IID random variables, we introduce the scaled epsilon v's.
So is rho v
It's the indicator function of the event that v belongs to you, y.
I see. So that is actually like a fair point toss. So it's like
Yeah, so it's a fair coin toss for if you interpret coin toss as a 0-1 random variable.
yeah, no, I got it.
Yeah, but then we want to scale this because
Because we want to
we know what the sort of absolute value of some of plus or minus one IID random variables is. This is sort of like just a technical tool to make sure that we sort of the degree deviation nicely pops out, and the rest is something that we can basically sort of point out from the existing literature that this is known what this expectation is. You could, in theory, explicitly extract those terms when working with rho v's, but that would be sort of a bit of a pain.
I don't get where the square root coming from. The last
Here.
quality, right?
Here, or
Right.
so 1 minus p is just a constant. So this is the expectation of the absolute value of so it's a standard fact that if epsilon 1 up to epsilon n are IID plus or minus one random variables, then the expectation of the absolute value of some of them is I believe root n over 2. And that's basically because this is the binomial distribution which sort of approximates Gaussian, so this is the standard deviation. So if you here wanted to have inequality and a constant, which is all we need, I imagine that there are some sort of much more direct arguments implying it. But actually, in this case, you can also just find an explicit answer for what this expectation is. But basically, the point is, this is a very natural thing to expect as the expectation. And or in this step, it's roughly root pn by this heuristic that it's kind of like a binomial random variable with parameters pn that we should be expecting as the answer. This is verifying the heuristic, and because we might have degree deviations, we have to be a little bit more careful. But this is sort of hidden in this argument is also the fact that for this to be extremal use of like type-ish, you can't have too many degrees which deviates by too much, because otherwise those degree deviations will already give you way too much access.
Can you repeat this argument for when G has an edge rate of positive layer, and then just like linearly move these variables epsilon low and blah blah to plus minus 1 by linearity? So even if G was not just a simple graph, but has a real positive real number between 0 and 1 as an edge rate,
Yes.
can we repeat this argument by somehow moving this low and epsilon linearly before argument? So
I got a bit also. What's the so you are interested with in which range of P this applies to, or what's?
So if like if G was a weighted graph.
Oh, if G was a weighted graph.
Yeah. With only edge rate.
There's a weighted version of this one as well, and things work out in a fairly similar manner on top of my head. I think you want to make sure that your edge weights the sum of their absolute values is something like proportional to n-choose 2, though. Because basically you could view this as a weighted version where we assign weights E for every edge and weight 1 minus P for all the non-edges. And then let me come back to this later. I think it's maybe during the break, because I got open it. But yeah, the weighted version of this exists as well.
So throughout this informal process, is there a place which is clear that we need the P is bounded away from 0 and 1?
Yes. It's hidden in this argument because at the very end, I get this bound for one of the terms, and for the other term. And my total bound for the contribution of vertex x is basically proportional to the sum of these two terms. And now the question is, when is this minimized? And there we say that it's minimized when d of x is close to p times n. Now, if p is little o 1 over n, this guy just lies between 0 and 1. So what actually happens is that we just say that it's minimized when d of x is 0 or 1. And there we actually see that in both that it's not the case that the contribution is lower bounded by root p times n, because you the contribution for those with degree 0 is just p times n, which is much smaller than root p times n when p times n is little o 1, which happens in this regime. So, I mean, the regime when p is constant divided by n is somewhat uninteresting, because basically there we are claiming that this excess is linear in n, and that I believe we could just gets somewhat by these rounding errors, because like if p times n minus 1 is not an integer, then basically all of these are constant, and if it happened to be an integer, then we can still use this bound to get some information out of it. But in the case when p times n grows with n, then actually it's really the case that the optimization problem is generally interesting, and there we see that this term starts dominating, and that's why I get the root p and contribution for each vertex. But yeah, it's basically in this optimization step where the condition is needed. Okay. So if both positive discrepancy and negative discrepancy are at least some small constant times this expression, then we are trivially done, because both of them are fairly large. So I have to say that the positive discrepancy is small. And I don't want to quite say that X union Y be a partition where this lemma is satisfied, because we're gonna did a little bit more than that. But let's for starters assume that this is the case. But we'll also add some more assumptions along the way. So then there are sets x and x minus, x plus and x minus. The x plus is the set of those vertices V, such that they see more neighbors in Y than expected, and x minus is x minus x plus. So let's also define this of UW to be number of edges between U and W minus P CW. And then we suppose that this is large, and sorry, this. This seems like a bit of a weird assumption to make, that the discrepancy of zero, y is zero. What we are actually doing here is that we assume that some sort of a linear combination of the discrepancy of y and discrepancy of x plus y is at least this bound. That's certainly fine, because the expectation of the discrepancy of y is just zero, because it's a random set, and the expected sort of a discrepancy weighted to the absolute values between x and y, one we consider in lemma, is large. The expected discrepancy between x and y is zero again, because it's a random bipartition. So the expected discrepancy between x plus and y is going to be at least this guy. So these are assumptions that we can certainly make in sense when we consider linear combination. This is just for intuition. So what should we do? We should really move the vertices from x plus to y, because that gives a set with large positive discrepancy, right? Because these guys have a lot of these guys have a lot of x as neighbors in y. So if you move them here, the edge axis in y should increase. And we know that the discrepancy of x plus and y is fairly small, because the positive discrepancy is small, which means that actually our heuristic was incorrect. And the only reason why it can be incorrect is because x plus lacks a lot of edges. So if we take the union of x plus and y, what's going to be the discrepancy of this union? Well, it has something to do with the edges inside y. Edges going across, we know there are many of them. Here we know that this is roughly the expected number. Between, it beats the expectation. If the total is not going to be too large, which we are assuming, then it means that here we must lack a lot of edges. So that should mean that x plus has a, in absolute value, large negative discrepancy, because it has to sort of counterbalance between the stuff over here. So an exercise is to prove if you have a union of disjoint sets, then this relation holds. So if you now apply this to x plus on y, we get that so this is so we made this rather bold assumption this is 0, which is just for the intuition. So we see that, so this is bounded by the positive discrepancy, and this is of the order beta times p minus 1 and 3, where beta is the constant given by this lemma. But that's kind of sad, because all we can conclude is that because this has a growth rate strictly less than that term, we see that this has to be at least negative the middle term, but that's not quite enough, because we would need the negative discrepancy of this to be minus alpha times this bound to ensure that the product of positive and negative discrepancy is large. Yes.
So discrepancy of with one set is an absolute value of the discrepancy, and discrepancy between two sets is naively
So here,
relative.
discrepancy doesn't have absolute value. Just remember that. So discrepancy is just for a set,
Yeah.
which is divided to be this guy. So here, everything is just without absolute values. So this guy, we know that it can have very large negative, so in absolute value discrepancy, but the positive discrepancy can't be, this can't be a large positive number. We know that this is a large positive number. We know that this is 0. So this must be a large negative number of scale this guy, because this positive number is much more smaller than that one. But the problem is that we would like this to be minus alpha times this number to ensure that the product is at least this guy squared. Because remember that our positive discrepancy has this 1 over alpha proportion. Here alpha really can be something that depends on n, because we are asking how badly do we fall short this average bound. So this is not going to be enough. So how do we sort of circumvent this problem? it's kind of like this is ingenious idea is to actually move less vertices across. And why does it work? Because sort of the discrepancy of a random subset scales quadratically in the probability that we sample with. So if y is a subset of x plus, so that each x in x plus is included in W independently at random with probability q, then the discrepancy of W is just going to be q squared times the discrepancy of x plus. Why? Because for every edge, the chance that it survives in W is q squared because we need both these endpoints to survive. And then what is W choose 2 is just the sum of the. So W choose 2 is just the expectation of summing all x prime in x plus, which are distinct, indicate a function of x in W. Prime in W. And because we are summing over all distinct things, these are independent, and by linearity of expectation, each of these terms is q squared, and they are exactly x plus choose 2 of well, I guess here, because I'm taking the half away, there are x plus times x plus minus 1 of them. So really, this binomial expectation of this binomial coefficient also scales as q squared. So this is exactly q squared, no rounding error included. Sorry, so here I should have the expectation. What's the expected discrepancy between W and Y? It's going to be q times the discrepancy between x plus and W. Again, for a similar reason, but now it's actually much easier. And this is going to solve all of our problems by taking q to be 1 over alpha. Let me actually now write down the proper argument because we have given the heuristic. Because the point is that now we move a much smaller set across. The smaller set which we move across must have which is chosen with q equals 1 over alpha. Then where did I throw these heuristics? Yeah. So here, because we are replacing x plus by W, so if q is 1 over alpha, this term is going to be roughly beta divided by alpha. And this guy is going to be roughly 1 over alpha. So as long as the constant c is large, this term still dominates the left-hand side. We need this guy to be proportional to 1 over alpha times this guy. But this guy is going to be 1 over alpha squared times the positive discrepancy of x plus. So discrepancy of positive, so the discrepancy of 1 over alpha squared times the discrepancy of x plus. So by absolute value, the discrepancy of x plus must be alpha squared times this number, which is alpha squared times the root p and q expression we want to. And it also has to be negative, so then we get that. Okay, so let me now write the formal proof. So suppose these assumptions I wrote earlier hold. So positive discrepancy is at most c over alpha times this guy, and beta is the constant given in the lemma. So we pick q to be 1 over alpha and choose x union y so that at random to the yes, so I want the discrepancy of x plus y plus alpha times discrepancy of y is at least b times square. And this is possible as the expectation of this guy is at least that by the lemma, and because the expectation of the discrepancy of y is 0. So yeah, sure, our assumption that the discrepancy of y was 0 might not be realizable, but actually what we care in the proof is how large is its linear combination for this particle to alpha. It doesn't matter because it sort of gets hidden in the linearity of expectation. But this is kind of morally how the argument goes. So that's why I sort of presented this sketch under these dubious assumptions first. And why is the expectation of the discrepancy of x plus and y large? Because we know that the expectation of this. Okay, maybe I should add a constant of 1/2 here. So this expression is just going to be the left-hand side of the lemma, because in this sum, all the terms are actually positive by the definition of x plus, because they see at least p times y neighbors in y. And over here, all the terms in the sum are negative, because they see less than that. So here I'm using the fact that I can write discrepancy of u and w as sum of u in u, how many neighbors it has in w minus the average. Because if we sum these terms, they give us exactly the edges between those two sets. And when we sum these guys, this gives us p times u times w. And now when we add absolute values around it, we get the statement of the lemma. And we can do that because here we have just gathered those terms where this every term is positive, and here we have gathered every term where the terms are negative. On the other hand, the expectation of the sum is just 0. So hence, the expectation of this difference is just twice the expectation of this first term. So really the lemma implies that the expectation of this guy is large. So there is an instance where this term is pretty large. We picked W as before, and we said, it's said to be Y union W. So we know that the discrepancy of Z, well, now Z is actually a random set, so, but we know that the discrepancy of Z is always upper bounded by the positive discrepancy, so we get this bound for the expectation, and this expectation is just gonna be discrepancy of Y plus Q times, so 1 over half times the discrepancy between Y and X plus 1 over half squared. That's the discrepancy of X plus. And we know that this is at most 0, where alpha times is bound. And we know that this guy is at least beta divided by 2 alpha times. This guy. So now if we choose C to be, let's say, beta divided by 4, we're just done. Because then this guy over here is going to be half of this term. So for this inequality to be satisfied, we need this to be roughly minus this term up to a factor of half. For that to cancel out the two, because this is now too large for this inequality to be satisfied unless this is large by absolute value and negative. So basically, if I write A for this number, then the inequality I'm having here is A is at least 2A plus something. And A is not positive. So this really means that this has to be at most minus A for this to be satisfied. But this has to be large by absolute value and negative. So this has to be at most so the negative discrepancy is at least alpha times C times this guy. Which implies that their product is large.
Well, I have a stupid question. Like, the expectation of this frequency of Y is 0. Is that because Y is a random
Yes.
bipartition?
Yes. So it's a random set, so the expectation, like because Y is a random set, so the expectation of the discrepancy is 0. Because the P times Y choose 2 is exactly the expected number of edges you see in a random set of size Y. Okay, so let's have a short break. I think 5 minutes. If you have any questions, I'm happy to answer them during the break as well. So, as said last time, Scott has some nice consequences. Stability for the discrepancy. So we know that the discrepancy is at least constant at root P and cubed. And if the bound is tied up to multiplicative constants for our graph, then both positive and negative discrepancy has to be large. It also implies the linear lower bound for positive and negative discrepancies, because the positive and negative discrepancies are upper bounded by P times 1 minus P times n squared. Yeah. However, it sort of still doesn't answer the question, how small can the positive discrepancy be? Because we have seen that it can be small in theorem graphs, but still the lower bound doesn't deviate away from the linear, and we'll hopefully see towards the end of the week an improvement of the linear lower bound in certain regimes.
So let me ask a question. Is it meaningful here they consider the product of the positive and negative? Is it meaningful to consider some other function of these two? For a simple example, we assign different power in the product.
On the top of my head, I would say that a lot of them are kind of ruined by this example that we have to run graphs. That basically, like we have this. I mean, the main question really, I would say, was that we have this trivial lower bound, and imagine we have a regime where p is a constant, we have a constant sort of density bounded away from 0 and 1. Now the discrepancies are between n and n squared. We know that those types of bounds are tight, but we don't know if the linear bound is actually tight for all the constants. We know that it's called tight for 1 minus 1 over r or 1 over r, depending on whether we consider positive or negative discrepancy or what happens in between. We know that the sort of middle ground is tight because we can take random graphs and they have discrepancy at the 3 halves. I think it's there are no sort of meaningful functions which are not optimized by either them being the same or them being sort of far away from each other. So at the other extreme where one of them is as small as possible and one of them is as large as possible. And it's really about what's the actual minimum that can be attained. Because that was a guess, and it was proved to be correct that actually depended on your density as well. So for some densities, the linear bound was tight, but not for every density. I think that's why it's that variant is likely ruined by the fact that we previously didn't know how small it actually can be in reality. Okay, so now we're going to change for the last 10-15 minutes the topic a little bit. So we go back to max cut. The max cut problem can be phrased as an optimization problem. So we can find we can assign every vertex either -1 or 1 with A, say, corresponding to those assigned value -1 and B corresponding to those assigned value 1. And now there's a very easy way to sort of describe where there are edges in the cut. If xi(xj) is 1, then it means that xi equals xj. So it's not in the cut. But if xi(xj) is -1, then it's in the cut. So basically half times 1 minus xi(xj) is the 0, 1 sort of a indicator function of the condition is ij in a cut or not. Okay, so here we are optimizing over the discrete set -1, 1. So basically we have 2 then choices. No improvement yet. But we can actually relax it so that xi's are now between -1 and 1. And allow sort of fractional values or decimal values over here. It doesn't really change the optimization problem. Well, certainly there's an inequality going this way. So any choice of xi's in the discrete set -1 and 1 is a suitable choice over here. But actually, the extreme attained on the right-hand side is always attained at the endpoints. And there's a very simple reason behind it. Namely the fact that if I fixed a variable xi, then this function is going to be linear in xi. So there's no quadratic terms or so on in this function. So for xi, the function is going to be something that depends on the other variables times, so it's going to be some constant, I think it's -half times xi times those j for which ij is an edge, xj. Now if you fixed all the other variables, this is just going to be some constant. If it's non-zero, then the sign of this already determines of whether we should pick xi to be -1 or 1 to maximize this function while keeping the others fixed. If it's 0, then we can basically choose value of xi anyhow we want to. In particular, we can choose it to be one of the endpoints. That kind of corresponds to a case that in it doesn't matter which side it is because there's the equal number of neighbors on both sides. So we are free to assign it. So basically, the extreme over here has to be assigned at the endpoint, so it's the same optimization problem. So a little bit, very little bit, about the algorithmic aspects. This is something called linear program. It's hard to compute. And there's no efficient way of solving, like finding this maximum in general. So if we wanted to develop an algorithm that calculates the max cut quickly, this is not a good way to go. That's why Goemans and Williamson introduced so-called semi-definite relaxation. So we consider the same problem, but now we pick some capital N as our dimension and look for vectors, unit vectors.
Well, sorry, is there a necessary to use soup instead of max? I think that is still continuous function on compact set. So
yes, I just wanted to be sort of as I said, these two are the same optimization problem because the extreme over here is so yes, you could use max because of that reason as well, but like same over here below, I think, but it doesn't really matter. So you could change the max instead if you wanted to. Okay, so here we fix some capital N. Actually, we can choose capital N to be small n because basically n vectors always live in n-dimensional subspace. So adding more dimensions doesn't really give us any advantage. And we define the problem similarly. Apart from now, our xi's are no longer real numbers between -1 and 1, but they are replaced with unit vectors in some n-dimensional sphere, and the product is replaced by the inner product. So obviously, so what's the motivation behind this? This is something called semi-definite optimization problem, and they are fast to compute. So determining the sub can be done quickly. So I think there are polynomial time algorithms to do that. So basically, if we can, so we know that our max cut is upper bounded by the semi-definite relaxation of it. But that's not really useful because we want to find lower bounds for the max cut. But now the question was, is this lower bounded? And turns out it is. Where C is some constant, which is roughly 0.868. So pretty good as well. And actually, there is the exact point where x constant for with this hold comes out from the proof. I will not show it, but I'll show the sort of surplus version of this for which I also prove. And this constant comes from optimizing some trigonometric functions. And quite surprisingly, the proof is a really nice method, and it's not particularly difficult. But the constant is actually assuming some central conjectures in complexity theory. This is it will be the best possible constant, assuming those conjectures are true. So actually, this has some deep connections to other important problems, which I'll not talk about any further. But that's not really useful for us because in the regimes we are interested, we want to look at the surplus, which is the max cut minus half the number of edges.
Sorry, the constancy is dependent on the capital N?
No, the constant C is independent. So it's 0.868. So it doesn't depend on M. But remember, the max cut is in the regime we are interested is going to be half M plus a smaller order term. So now what this is implying is that this is really useful only in the regime where the max cut is much larger than half M.
Yeah.
So that was the comment I was about to say now, that for our purposes, when we are interested in the surplus, this is not particularly interesting because this sort of 1 minus C bit will be it will sort of destroy any of our hopes to get anything useful out of it. That being said, the method that they use to prove this result applies to surplus as well. and I'll now state the variant. So assign a unit vector Okay, so this looks weird. There's a very natural geometric region of white holes. Intuitively, I would just pretend that arc sin of x is x. Sadly, that's not true. In real applications, what you do is that you split your inner products into negative and positive ones, and you apply lower bounds in both regimes, with slightly different content, and there's a lot of technical annoyance going on. Usually you get the right intuition by doing this approximation. Sometimes you have to be so miserable that you have actually do tailor order approximation to a higher order term, so you get sort of xu/xv cubes inside of your expressions, and that's really complicated. But in the applications we are going to do, you should just think arc sin of x is x, and then hope that the details will be smooth enough that they won't matter. Or some constant matters.
There's no shop in any case.
Sorry?
There's no shop in any case. Is it shop in any case? It's because the arc science seems very weird, right?
So this gives things which are sharp up to multiplicative constants.
Oh, okay. Thank you.
Well, what is so is 1 over what?
Minus 1 over pi.
Pi. Oh,
Yeah. And I have 2 minutes. That's probably enough actually to prove it. So you should really not think this as a sort of an expression that is your target is to reach this one exactly. But what actually is that, like, whatever comes out of the proof applying Goemans-Williamson method for the surplus is the right thing to consider, and this is just what happens to come out of it. So the method is very nice and simple. So given such vectors, we pick W in the unit sphere uniformly at random. And we let A be all those U for which the inner product with W is non-negative, and B the big A component. So essentially what happens is that we have a sphere. We have these vectors x, v1, v2, v3, and so on pointing on. Then we pick our random W, which is some direction. Then we draw the plane that is orthogonal to it, and that plane determines the cut of the sphere. And the cut in the graph will be those vertices which are in one side of this half sphere generated by this plane orthogonal to W. And we claim that this is just the expected size of the cut. We can decompose W as W is naught plus W1, where W naught belongs to the span of XU and XV, and the other bit belongs to this the orthogonal complement of their span, which basically reduces to a 2D problem, because with high probability W0 is actually with like the probability that W0 is a zero vector is 0, so we can just ignore that case. And conditionally it being non-zero, it's just the scaled version of it as a unit vector is just uniformly distributed on the unit circle. So we basically reduce it to a 2D problem. And in 2D problem, these are the two intervals that are suitable for W0 to live in. Because if it's over here, then we know that V belongs to the cut, but U doesn't. And if it's over there, then here, then U belongs to cut. U belongs to A, but V doesn't. So these two sectors are the only ones where the edge UV belongs to the cut. And alpha is just the Argus cosine of the inner product. So this is just 1/2 minus the Argus sine. The inner product. Divided by 1/pi. As the inner product is just cosine of alpha. And now the half cancels with them over 2. So we are left with this minus 1/pi times the arcsine of XU inner product with XV. So basically, if we have a suitable collection of these vectors, then this is going to be the expected size of our cut. So there is a cut, which, well, it's expected size of surplus, so there is a surplus beating this. So now it's a very good question that is this tight, because this looks like a terrible thing to do, because we are basically saying that linearity of expectation should give us something that is tight, which sounds tricky in general. The thing is that this is going to be useful when we pose some additional conditions. So for example, this can be, so at the start of next lecture, we'll see why this gives good bounds, and actually tight bounds in some regimes, for graphs which are surplus on the graphs that are triangle free. Because basically, how we usually would pick R of n be indexed by the vertices G. Then we pick XU W to be something which has information on both U and W. And then the inner products will be sums of this form. And because we care about those inner products which correspond to edges, then our inner products will have terms of the form XUW times XBW, where U and B are also an edge. So now if XUW, say, depends on the status of whether UW is an edge, all of a sudden XUW times XBW is somehow connected to the fact whether UVW form a triangle. So actually making clever choices of these vectors can somehow sometimes give you tight surpluses, because think of it in this way: you essentially want to make sure that edges correspond to negative inner products, which means that basically you want your vectors to be roughly orthogonal, but so that they have very slight negative correlations along the edges. And because our surpluses are usually going to be small, maybe there are clever choices for these vectors, especially when we pick our space to be very large. so that these small negative correlations actually sum up to proper surpluses. But I'll continue from that tomorrow. So tomorrow we'll see how to use this to get tight bounds for a surplus on triangle free graphs, how to get tight bounds on positive discrepancy for very sparse graphs. There's also a positive discrepancy version of this. And then if we have time, we discuss a little bit about bounds for lambda 2 when d is greater than 1/3.
So is the theorem called Williamson?
So this one is called Goemans Williamson approximation algorithm for the max cut. They didn't have the surplus variant, but this is basically this argument. Let A and B be chosen. Like this is, I would say that this is called Goemans Williamson method or Goemans Williamson rounding method, because this is basically how this was used in the study of surplus was that people noticed. I mean, obviously it's related to the max cut problem, so people noticed, okay, this method which is used to find algorithmic lower bounds for max cuts actually also works in the surplus case if you run the proof again. And then if I would say that the usual it's just called Goemans Williamson technique or method or surplus rounding method, because you sort of then have to do this approximations on how to estimate the August sun. Their paper didn't address the surplus regimes, but it's more that their motivation came from the algorithmic aspect, so they didn't really care about this question.